Hi everyone, Mrs. V here, and today we are going to be talking about how you calculate the pH of weak acids. This is definitely one for the whiteboard, so let's get started.
All right, this is going to be part one of the relationship between Ka and the pH of weak acids. And this is going to deal with if you're given the concentration of a weak acid and its Ka value, how you determine its pH value. Now I have an example here. We're going to calculate the pH of a 0.100 moles per litre solution of acetic acid when we're given that the Ka value for acetic acid is 1.8 times by 10 to the minus 5 at 25 degrees Celsius. And let's have a look at what we know. Acetic acid is CH3COOH. And we talked about this example before. We talked about this being the acidic hydrogen. And so this is actually a monoprotic acid. Let's write the equation for its ionization. So we have an equilibrium set up between acetic acid and water and the acetate ion and the hydronium ion. If we want to calculate pH, this is what we need to calculate pH. And we need to find that. We need to find the concentration of H3O+. Because of course our pH is minus the log of concentration of H3O+. But in this case, we cannot say that the concentration of the hydronium ion is equal to the concentration of the acid, because we're looking at a very weak acid. If we come up and look at the Ka value, that's a very small value of Ka. The equilibrium does not lie to the right in this. In fact, it seems to lie a long way over to the left with such a small Ka value. So we need to develop a method that doesn't depend on the equivalence of concentration that we saw with the strong acids. So here, our concentration of hydronium ions is not equal to our concentration of acetic acid. And that's because it's only partly ionized. The position of equilibrium lies well to the left. And we know that because Ka is so small. So we're going to need to have a different method for doing this type of calculation. In this case, we're going to use an ice table. We're going to say that initially, let's write our equation so that the things that are in the Ka value will be acetic acid. There will be no water because that's a pure liquid, so that won't appear in Ka. And if we look at our initial concentration, we started out with 0.100 moles per litre and none of this. Then at equilibrium, we're not given the concentration of anything. So why don't we just let the concentration of the hydronium ion, let's let that be X. So if the equilibrium concentration of the hydronium ion is X, then what has the change been? Well, we've gone from 0 to x, so we must have added x. If we added, because there's a 1-to-1 mole ratio, every species in the equation has a coefficient of 1. So we've got a 1-to-1 to 1-to-1 mole ratio. So if hydronium ion goes up by x, then the acetate ion must go up by x as well. And so its equilibrium concentration will be x. On the other side of the equation, we also have a 1-to-1 mole ratio with acetic acid, but because it's on the other side of the equation, that's going to go down by x. So its equilibrium concentration is going to be 0.100 minus x. Now, how does that help us? Well, we can write an expression for Ka, which is the equilibrium constant. And that is going to be the concentration, remember, products over reactants, concentration of the acetate ion, concentration of the hydronium ion, all that over the concentration of acetic acid. But in this example, if we just jog back up to the example, we're told the actual value of Ka. So we're told that that's equal to 1.8 times 10 to the minus 5. Now we can do some substituting of the values from our ICE table. So concentration of the acetate ion is x. We're going to multiply that by the concentration of the hydronium ion, which is also x. And the concentration of acetic acid is 0.100 minus x. And that's going to be equal to 1.8 times 10 to the minus 5. If we collect all of our terms here, we have x squared over 0.100 minus x, and that's equal to 1.8 times by 10 to the minus 5. Now, what you could do is you could sort out this into a quadratic equation. So if we took that, we could go x squared equals 0.100 minus x into 1.8 times by 10 to the minus 5. We could multiply that out, collect like terms, and solve a quadratic equation, and we get some values for x. So you can do things that way, and I can promise you that that is going to be some nasty numbers. So what we actually do is we notice that because the position of equilibrium lay well to the left, x is going to be tiny. I mean, have a look. The value of this equilibrium constant is 1.8 times 10 to the minus 5. X is mighty small. So what we're going to do here is notice that for the purposes of the order of magnitude that we're dealing with, 0.100 minus x is approximately equal to 0.100. And that's because x is so small. So what we can actually say then, we can have x squared, and we just replace the 0.100 minus x with 0.100. From there, it's just a much simpler equation. So multiplying both sides by 0.1, we have 1.8 times by 10 to the minus 6. And then taking the square root of both sides, we get x equals 1.3 times 10 to the minus 3. Now here is your trap for young players. You can't stop there. You found X, but the question didn't ask you to find X. The question asked you to find pH. So you must go on to find pH. You'd be surprised how many exams I mark where the story stopped at X. This is not what you've been asked. So looking back, what was X? X was the concentration of H3O+. So what we found here is the concentration of H3O+ is 1.3 times 10 to the minus 3. And that will, of course, be in moles per litre. So we need to now, for pH, take minus the log of that. And your pH comes out to be 2.9. So that is the method that we use always for finding out the pH of weak monoprotic acids. And it doesn't matter what your acid is in this original equation. It could be acetic acid, it could be carbonic acid, it could be any of the weak acids, citric acid. The main thing is that you follow this exact same process every time, and that is how you determine the pH of the acid. That's definitely enough thinking for today. So I am going to see you in the next video when we are going to look at how you calculate the concentration of H3O+ and then go on to calculate Ka if you're given the others. I'll see you in the next video.